Okay, thank you, I forgot to ask. Yeah. All right, so the homework that'll be due next Monday. And by the way, I think we only have this week, and then one more week, and then it's finals week, right?
Yep.
So 2 weeks, yeah. And of course, we're probably gonna have to review for a day or two before final. So this will probably be the last homework. Maybe I'll be able to squeeze in a few extra problems. I'll do my best to do that. But homework due next Monday. Problems 17.1, 17.2, and then 19.2 through 19.10. Okay. So that's chapter 17, problem 1 and 2. And then the others in chapter 19. I'll have the test graded soon. I've graded the first 2 problems, and then partway through the third. So we'll see where you stand and hopefully pretty soon.
So I think.
Okay, first thing we got to start with is our definition of temperature. You're probably pretty familiar with Fahrenheit, right? Unless you're from most other countries. So definition, so Fahrenheit is defined to be that temperature at which water at atmospheric pressure. I'm just going to write 1 ATM, that means atmospheric pressure. Freezes at 32 degrees Fahrenheit and boils. What's the boiling temperature of water? 212 degrees Fahrenheit. So the temperature range in Fahrenheit degrees between boiling and freezing, 180 degrees Fahrenheit between boiling and freezing. And boiling. I guess that's sort of how it's defined. Somebody told me once that the reason why Fahrenheit came up with with the temperature stuff had something to do with the fact that the body temperature should be 100 degrees. And he found that most people's body temperatures and he thought most people's body temperature was 100 degrees, and I guess his temperature always ran high. So, you know, that kind of makes it annoying as a temperature scale, actually, because there's no good even numbers in this. The more common type of temperature scale for scientific purposes and also around most of the world, Celsius scale. And how's Celsius defined? Anyone know?
Freezing is 0.
At water at one atmosphere. Freezes at 0
Degrees.
freezes at 0 degrees Celsius and
Boils
boils at 100 degrees Celsius. So that's actually a pretty straightforward temperature scale, isn't it? I mean, I don't know, this one's pretty nice as far as even when we're dealing with water. Much of our world deals with that. So let's go ahead and see how we can convert between these two. Okay, so the temperature range between freezing and boiling in Celsius, 100 degrees Celsius between freezing and boiling. So if I want to take a Fahrenheit temperature and convert to a Celsius temperature, what do I have to do?
Take 9 times.
All right, so
times the
let's,
Celsius.
let's go one way. Let's say I have 10 degrees Celsius. Let's do this way. How do I get it to Fahrenheit?
Wouldn't it be Fahrenheit equals 9/5 times the Celsius minus 32? Or is it plus
Is that the
32?
formula?
I think so.
I always have to just look at this.
Oh, okay.
Is what I always do. And I go, okay, so freezing is at 32 degrees Fahrenheit. Okay, it's 0 degrees Fahrenheit. So this is 10 degrees Celsius above freezing. And for every degree Celsius, it's 1.8 degrees Fahrenheit. Okay, you see that? Because it's 180 degrees Fahrenheit between freezing and boiling, and Celsius it's 100 degrees. So the Fahrenheit degree is, or the Celsius degree is 1.8 Fahrenheit degrees. And so what I'll do is I'll just say, okay, if this is my temperature in Celsius, I'll add 32 degrees to it and multiply by 1.8. So what I'll do is, this is 32 degrees Fahrenheit plus 1.8 times the 10 degrees C. And this would be degrees Fahrenheit per degrees Celsius. And I'd see that then this is what, 50 degrees?
50 degrees, yeah.
50 degrees Fahrenheit.
So for every temperature of Celsius, if we multiply it by 1.8 and then added 32, it will work
Yep,
every time?
every time. Sound good?
Yeah, that's like that.
So let me give you one on your own, see if you can get this one. Let's say I have negative 10, or let's not do something dead even. Negative 18 degrees Celsius. Go ahead and convert that to Fahrenheit. Let's see. Trent, you get it?
Yeah.
What do you get?
25.
25?
Yeah.
64?
Yeah.
Not negative .4.
What?
Negative .4.
Or negative 0.4.
Well, something's kind of going weird here. All right, so let's just we'll do it just very. All right. So what you do is you take 32 degrees Fahrenheit. Just take that plus 1.8 degrees Fahrenheit per degree C times whatever the temperature is in Celsius. Negative 18 degrees C. It doesn't matter whether it's a positive or negative sign. You just put whatever the temperature in Celsius was. All right, so what was that?
Negative .4.
Negative 0.4?
Yeah.
Okay. Good. Everyone see how to do that?
Mhm.
All right, let's see if we can invert that process and go backwards now. All right, so 2012, Hayes had a pretty hot summer, and at one point it was 113.6 degrees on June 26th. So let's see if we can do 113.6 degrees Fahrenheit. Let's see if you can convert this to degrees C. So let's see if we can figure out how to do that. Okay? You got it?
Yeah,
All right. What do you get?
45.3.
Okay, did everyone get that? 45.3 degrees Celsius. All right, let's go see how to do that. So, I'm gonna just look at this way that I converted it. So I'm just gonna write the temperature in Celsius. The temperature in Fahrenheit is equal to 32 degrees Fahrenheit plus 1.8 degrees Fahrenheit degrees C times temperature in Celsius. That's my formula for the conversion between the two. Let's just solve for the temperature in Celsius. So temperature in Fahrenheit minus 32 degrees Fahrenheit is equal to 1.8 degrees Fahrenheit over degrees C. Temperature in the Celsius. Divide through by 1.8 degrees C. And you get that the temperature in Celsius is the temperature in Fahrenheit minus 32 degrees Fahrenheit over 1.8 degrees Fahrenheit over degrees C. So in my case, 113.6 minus 32 divided by 1.8, and that would be degrees C. And it should turn out to be roughly 45.3 degrees C. Make sense? All right. There is one more, even more scientifically useful than Celsius temperature scale that we use on a daily basis, and what's that?
Kelvin.
Kelvin. Good bit. Now, I hope we'll get a little bit of time to go into what temperature actually means kind of at the molecular scale, but we may not. Roughly, we can say that temperature is a strange unit for the average kinetic energy of the molecules that make up the substance. That's a roughly what temperature means. So if I have some sort of absolute scale of temperature, I might be able to say that 0 temperature would mean 0 average kinetic energy. That would mean no movement of molecules. If I double the temperature, I double the average kinetic energy in that absolute scale. And so that creating some sort of absolute scale of temperature is the idea behind the Kelvin scale. Strangely enough, we don't ever talk about degrees Kelvin. We just talk about Kelvin. Okay? I don't understand quite why, but that's just the way it is. What it is, the spacing between the degrees on the Kelvin scale, or the kelvins, same as that for the Celsius. 100 degrees between freezing and boiling for water. But the starting point of the Kelvin scale is quite different. And it starts at where the at what we call absolute zero, where there's no kinetic energy of molecules. What's that absolute zero? Does anyone know?
273?
That's right. So 0 Kelvin is equal to negative 273.15 degrees C. Okay. And spacing between Kelvin, spacing on Kelvin scale is the same as the Celsius scale. Same as Celsius. And so what I would do if I wanted to get to the Kelvin scale is I would take the temperature in Kelvin would be the temperature in Celsius plus 273.15. Okay, that's because 0 Kelvin is negative
No,
273.15 Celsius. So for instance, what would be, so for instance, 0 degrees Celsius freezing would be 273 Kelvin. Okay. Boiling would be 373.15 Kelvin. Make sense? All right. So just out of curiosity, just so we know, what is absolute zero in Fahrenheit scale? Zero T. This is this means zero temperature, absolute zero. Means the zero temperature in Kelvin, K equals 0. Temperature in Kelvin is 0. And on Fahrenheit scale, question mark. So just make sure you get that, just to make sure you got everything down, see if you can get that.
Negative 459.
Yeah, that's what I got.
All right, so we'll do the temperature on the Fahrenheit is 32 degrees Fahrenheit plus 1.8 degrees Fahrenheit over degrees C times temperature in Celsius, which is minus 273.15. And if I plug that in, that would be what?
Negative
Negative.
459.67.
6, yeah, there's probably more. 6, 7?
Yeah.
Okay. No lower temperatures than that. Anyone know what the lowest temperatures that have ever been achieved are? Just so you know, lowest temperatures that have ever been achieved are roughly a trillionth of a Kelvin. The physics to get to that has been resulted in 2 Nobel Prizes in physics in the last over 20 years. And that involve laser cooling and optical trapping and things like that. Very, very cutting edge physics to get to extremely low temperatures. The reason is that matter behaves very strangely at such low temperatures, and that's why they want to get there. Okay. So now let's just go back to what we were talking about with gases and with pressures and stuff. We're gonna do more kind of straightforward thermodynamics. This is all temperature stuff. The typical thermodynamics problem is how come, in physics, is why does an engine work? You know, that's actually how a lot of thermodynamics got developed a long time ago. Was to understand how like the steam engine worked. Actually, it's interesting. One of the very first, great physicists, probably not known too much, was a guy named Sadi Carnot, one of the only great French physicists. His name was, he was he was an engineer around the time of the French Revolution. And he wrote a book called Reflections on the Motive Power of Fire. And he had no concept whatsoever of conservation of energy. They didn't know about that back then. And yet, somehow or other, he came up with this, what was called the second law of thermodynamics at that time, which was entropy. A lot stranger in many ways than the conservation of energy. But he did that and came up with what was known as the Carnot cycle before they had any idea of conservation of energy. And his book is a kind of, I have a copy of it, and it's a really quite a brilliant book. It's really neat to see how people were thinking back in those days. And they get it from the horse's mouth. So anyway, we'll leave that. The basis behind thermodynamics was the steam engine, is what people wanted to understand better. We won't do steam engines, we'll do a piston and a cylinder, because that's what I'm more familiar with. They use those for steam engines too, by the way. So let's consider a simple situation where we have a cylinder and a piston, and this cylinder is filled with gas of some sort that can be compressed. Let's say that there's a pressure outside on maybe the atmosphere or whatever, on the outside of this piston. And this piston is free to move up and down. Let's call the area of the cylinder head, area equals A, okay? Now let's say I took this, let's say that I had this cylinder head and it moved from this, I'm going to call this the initial and then this the final position. Let's say this is separated by a distance x. How much work was done by the gas inside the cylinder when this piston moved? How much work was done to move the piston? Well, actually it probably depends on the way that you move the piston. If I moved it very fast, I had to accelerate the piston. And so to move it this distance, I had to give the piston itself some kinetic energy and also move against this pressure. Okay? So that would depend on the mass of the piston. Let's assume that we move this very, very slowly. So move it very slowly from here to here, or that the piston itself is massless. Either one of those. If we look at that process, then you have a force that's pushing downwards on that, right? And if we want to move this slowly upwards, this gas would need to exert a force that would be equal to the force pushing it that way, at least. Does that make sense? So there needs to be a force exerted by the gas F, which would have to be the pressure, outside pressure, times the area. if I had a bigger force than this, pushing upwards on the cylinder head would accelerate, or the piston would accelerate. If I had exactly this force and slowly moved it upwards, this would work, right, as the force. That's because force, pressure, to remind you, is force per area. But this would be the minimum amount of force needed to move this upwards. Any less force in this, and this thing's moving the other way. If I have that force and slowly move at a distance x, how much work did the gas do? Let's move it from this lower position, initial, to the final. How much work did the gas do? Well, it's the distance. The work is force times distance, right?
Mhm.
So the work done by gas, where is this? Is equal to the force times the distance moved, the x, right? This would be pressure times the area times the distance moved. You see that? Now, if I wanted to look over here, that would be this volume, wouldn't it? And so this would be the pressure times that volume. I'm going to call that the change in volume of the gas. Does that make sense to you guys?
Why is it a change in volume?
So if I move the piston from here to here, the amount of volume that changed was that volume, which would be the A times that X. Does that make sense? And so the work done in an expanding gas is P times the change in volume, where the pressure is the outside pressure and is constant. So this is work done by the gas. Now let's suppose that I put a thermometer in here. Okay. Anyway, thermometer. Temperature, okay. If I put a thermometer in here, and as this process went on, what I would find is that the temperature would decrease as that thermometer was in there.
So is it as the pressure increases, the temperature decreasing?
Well, the pressure didn't ever change
Oh.
because it's working against this outside pressure. But the gas did some work. I'm going to say that these walls are insulated, so we're not worrying about heat from the environment flowing in there. Walls are insulated. Anyway. So as I put a thermometer in here and raise this piston, the temperature would decrease. And there's a way, we want to kind of understand why. If all I do is work, it turns out that the energy of the system, this is an experimental fact, but the energy of the gas is equal Well, the energy of the gas, if all I did was work, is equal to the change in energy, sorry. This is the final energy minus the initial energy of the gas. Final energy minus the initial energy of the gas would be equal to the negative of the work done. So if the gas did positive work, that means it did work to push that piston up. We find that the gas lost a certain amount of energy. Okay. So if I do positive work, if the gas does work, it had to take some of its own energy and give it to doing that work. There's a relation between this change in energy and the work that's done. And that is, it's found that the change that it's equal to some constant times the final temperature minus the initial temperature. Is equal to C times the final temperature minus the initial temperature. Or C delta T. And that turned out to be, and that is equal to negative the amount of work that was done in this process. Anyone know what this constant's called? This is called the heat capacity of the heat capacity. This is the internal energy. Sometimes, and actually probably most books, this E is going to be called U, particularly in chemistry. That's the internal energy of the substance. And then this is the relation here between the internal energy of the substance and the temperature of the substance. And we'll be using that. All right, let's see if we can do an example so we're going to get this straight. By the way, all the energies measured in what units?
Celsius, Kelvin.
Energies.
Oh, and it's, oh, joules, sorry.
All right, very good.
I'm
Because we're in SI units. A lot of times, and for historical reasons, you might see calories or something being used there, but we'll use joules. Okay. So, let's say that I have a piston here with a certain, the area of the piston. Let's do the area. At area equals 0.1 meters squared. So that's actually a pretty huge piston, but whatever. The pressure here is 1.0 times 10 to the 5th pascals. So close to atmospheric pressure. Let's say the heat capacity of the gas within here. So see how heat capacity is the constant between the change in energy and change in temperature. That means the units of heat capacity would be the units of energy per degree. So I'm going to say that the heat capacity in here, this is awful sounding.
Yeah.
By the way, the pressure, because the pressure here and the pressure here are the same, so we have equal, so the force is pretty balanced and we just move this slowly at a constant speed. This would be the heat capacity at what we call constant pressure. Let's say it's 100 joules per degree C. What this means is I have to add 100 joules of energy to this gas to raise its temperature by 1 degree C. And let's say that I did an amount of work, or I moved this distance 10 centimeters. My question is, let's see if we can get some more squeaks out of this. What is the final temperature? The temperature of the gas. This is good. John. Of the gas. Oh, by the way, let's say that this starts out at 300 Kelvin. 300 Kelvin is the initial temperature. What is the temperature of the gas after expansion? Question mark.
So it's gonna decrease, right? Like you said, the temperature.
All right, maybe we can do this as part B. Let's do part A as how much work is done. How much work did gas do? And these cylinder walls are insulated, so no extra energy gets in through the walls. See if you can get through that. Got it?
Is the work the same as the delta E? Like once you figure out how much work is done? Or do we have to figure out what delta?
Well, so the energy changed by doing this work. And is there any way that another way the energy changed? Yeah. Go up or down? The energy increase or decrease of the gas? Because it didn't work on the outside.
Do we have to change the degree Kelvin for the initial temperature to Celsius?
No, I could write joules per Kelvin here too.
Oh, okay.
Because the scale, the
It's the same scale.
same scale just shifted different. Get that? Let's see how to do that. Okay. So, how much work is done? Well, the work done by the gas is just P delta V. So that's 1 times 10 to the 5th pascals divided times the change in area in volume. Well, if the area is 1/10 of the square meter, and the volume and the height it moved up is 0.1 meters, right? Then the change in volume would be 0.1 meters squared times the 0.1 meters that it moved up. That makes sense? And so this would be 10 to the minus 2 multiplied together. 10 to the 5th, that'd be 10 cubed, or 1,000 joules. That makes sense?
Yeah.
Now the change in energy of the gas itself, because the gas did work by expanding into the environment, by forcing that piston up into the environment, it lost energy. So that'd be negative work, the work done by the gas, and that's negative 1,000 joules. Now, any change in energy of the gas will be related to a change in temperature. That'd be the heat capacity times the final temperature minus the initial temperature. The heat capacity is, so I'm just going to put minus 1,000 joules here like that.
Divided by the.
So this heat capacity was
100.
100. This is 100 joules per Kelvin. So divide through by that, and I get
Negative 10.
negative 10 Kelvin is equal to T final minus T initial. So that means the final temperature is down by 10 Kelvin from the initial. And so T final is 290 Kelvin. That makes sense? Good. Now, this would all be wonderful if everything were nice and insulated. But in reality, that's not the case. And in fact, maybe we don't always want it to be the case. There is another way for the energy of the gas to change. And this is for heat to flow from the gas or to the gas. So I'm going to introduce something called Q. And this is the amount of heat that flowed into the gas, or amount of heat. We have to kind of define it and talk about heat. Heat which flowed into the gas. Now, heat's another form of energy. If you think of it, Sadi Carnot back in the day, he knew about heat, and he pictured it as some sort of invisible fluid that flows into cylinders, and he was able to actually do most of thermodynamics with that. They called it the caloric. Now that's not, we know now that heat is more movement of, kinetic energy, the energy of the kinetic energy of the molecules, and that energy itself just kind of flows into things. But the details of it aren't important so much as just knowing that there's other ways besides that work being done on the environment for energy to change. So for instance, if I took my coffee there and just let it sit in the environment that coffee's not doing any work on the environment, is it? I mean, it's not expanding. It's not doing any work, but it is losing energy to the environment by cooling off. And that amount of energy that it loses by cooling, that will be the heat that flowed out of the system. That makes sense? So heat, stuff, energy transfer that's not being used to do work. And we can maybe think of it in that general way. So if we define this Q as the amount of heat which flows into the gas, if Q is positive, that gas is increasing in energy, right? And so I'm going to adjust this formula for delta E just a little bit here, and I'm going to say that delta E, any way that a gas can change energy, is going to be equal to Q, the amount of heat that flows into the gas, minus W, the amount of work that the gas does. This will still be equal to heat capacity times the change in temperature. Okay? Only now there's two ways to change energy of the gas. This is probably the most general, this is the general formula for this. This is actually a statement of what's called the first law of thermodynamics. First law of thermodynamics. This, what this says, is that any change of energy in a substance is equal to the energy that flows into the substance from outside in the form of heat, minus the energy that leaves the substance due to actually doing work. If I look at it in another way, any energy that's going in is either changing the energy of the substance or going back out again. If I think about that for a little bit, what this says is that I'm not creating any energy. All I'm doing is I'm making energy flow from either the environment to the substance or outwards. That's all. And the energy of the substance itself, whether it's a gas, liquid, whatever, is any change of that from this flow of energy into or out of the system. No energy is actually being created in the system. This is a first law of thermodynamics statement of conservation of energy. You can't prove it, it's just experimentally observed. And no experiment has ever been done that disproves that. So, from the smallest experiments to the largest.